So I was able to finish writing the solutions for the practice exams. So you can find them already here on Canvas. I also had to make a slight change to one problem on each practice exam. So just download again the PDF or check it again because there were two problems that they had to be slightly modified so that they would be a little bit more interesting. So yeah, that the practice exams already are here, and then I'll at least give you the solutions to yesterday's the quiz on Tuesday and today's quiz. I'll write the solutions and send them to you today, and I'll try to have the quizzes graded by tomorrow. So that you have all of that ready before the exam on Monday. Are there any questions about the exam? Well, it would be a similar format, but yeah, it will be structured in a similar way. It's just that they are like on the actual exam, you won't see the six questions at once because you see first three and then three. So it is two parts, except for that, it's more or less like similarly structured. So quiz one, I mean, exam part one or part one of the exam will become available at 1 p.m. and then you have 40 minutes to do that, 15 to upload the solutions, and then part two will become available at 2 p.m. and then you have 40 minutes to solve it and then 50 minutes to upload it. But yeah, except for that, I mean, it is more like the problems and things like that will be relatively similar to the practice exams. It won't be too different from like the examples we have been doing. I mean, so if you check the problems I have recommended for the quizzes and the examples we did in class and the practice exams, I think you'll be good to go, basically. I guess on Monday it won't make a lot. I mean, I'll be obviously I don't think it makes a lot of sense just to like start the Zoom meeting. So like the idea on Monday would be for you to, I mean the exam will become available at 1 p.m. So you can just start at 1 p.m. instead of like coming to the Zoom meeting, you can just like start taking the exam. Of course, like if something comes up, you can email me because I'll be like, checking everything, but I don't think it makes a lot of sense to open the Zoom meeting just for 1 minute. So you know what I mean? So but you'll find it like in the same place no you have found like the quizzes on Canvas, so it will be like right next to it. Is that okay? Any other questions? Um, but yeah, the exam will be like pretty similar to the practice exams and again the examples we have been doing in class, um, and the quiz problems or the problems I recommended for the quizzes. So let's see where is okay, good. So well, you'll have 40 minutes for each part and then like 15 for uploading the solutions to each part. So like it would take you like the 2 hours, but in terms of exam time, the exam time per se is 80 minutes. It is, as I said, each part is three problems, so I think you'll have like relatively sufficient amount of time for each part. It's not, I don't want to make it like too long or anything of that sort. So, um, So today, since we're starting a new topic, which won't be on the exam, I'm changing the PDF, so this will all be brand new on a separate PDF to not confuse things. So today we're going to talk about derivatives. And I'll try to do stuff that is related to to finding limits, which is something you need still to know how to do for the first exam. So I'll just try to explain the things that are more related to what we have been doing. So today, yeah, derivatives is one of the big topics in calculus. Like calculus is really always like two parts. Like the first part, derivatives, which is what we're about to talk, and the second part are integrals. Okay, so derivatives are really one of the two big components of calculus. So, in fact, like probably derivatives will eat up like half of this course. Like just talking about derivatives will be like half the course. Then there will be a like last part where we start introducing integrals. But if you take Calc 2, then that's where you will spend a lot of time like talking about integrals. So here, integrals won't play such a big role, but that's just because if you need to take Calc 2, then you'll see a lot more about integrals there. Okay. But so what, and like derivatives have a lot of applications, so we'll go into many of them like as the course progresses. But today I'll just start with the most just like the basic idea of where you can start talking about integrals, which is sorry, about derivatives, which is like about this problem about finding the tangent line. So that's like a easy like a good introduction for why would you care about derivatives. So here's like the idea, or here's like a problem you want to solve. I actually briefly mentioned this on the first day of class. You may or may not remember this, but the idea is like you have like the graph of a function of one variable, right? So you have the graph of y equals f of x, and this is the graph function, right? And then if you choose a point x, a value of x, you'll get a point on this graph, right? Which is x comma f of x. Okay, and the idea is like, and we'll go into more details next week. One would expect that there is a tangent line to this graph going through that point. So we're trying to find like a tangent line, which in this case does look like something like this. So we want to find like a tangent line to this to the graph passing through this point, let's call it point P. Let's call this point P, passing through P. And the biggest the important thing here is that to find a line, to find the equation of a line, what I don't know if you remember, we talked about this like the first time, but what do you need? You need the slope, and actually you need the, the equation of a line can be written in different ways. but definitely you need the slope. And for example, you need like the point on the line or the intercept, but it's more convenient to think about it as in terms of a point on the line. So we already have a point on the line because we wanted to go through this point P. So really the only thing that you have to worry about in these problems where you're trying to find the tangent line is to find the slope. So it all boils down to finding the slope. So the key things that you have to do, so, so what you need to do to find the tangent line, what you need for the tangent line, for this tangent line, is the slope. Okay, let me stop here. Are there any questions up to this point? Is that making sense? So, um, how are we going to find this slope? That's where the limits come in. That's the basic reason why we spend so much time talking about limits so far. So, like, let me remind you, like, and what was the idea behind this? So, let me go to GeoGebra. Just as an animation. Okay, let's see if I can show you the GeoGebra here. Okay, so imagine that I wanted to, I give you like the equation of y equals x squared, right? The graph of f of x equals x squared, that's a parabola, which you see here, right? Oops. Let me improve the graph a little bit here. Okay, this now looks better. Right? So that's a graph of y equals x squared or this parabola. And let's say that I wanted to find the tangent line at a point. So the point that I may want is the point. Let's see, what's the point on this parabola? It could be the point 1 comma 1, right? So I give you P, which is 1 comma 1, right? So that's a point on the parabola, and we want the equation of the tangent line. Okay. So again, the philosophy of calculus is that you, instead of like to find this equation of the tangent line, what you do is choose another point on the curve. Okay, so what's another point on the curve? So like let me write it as q. So I'll just write q to be 1 plus h comma 1 plus h squared. Okay, so I'll explain to you in a moment like what this h is, but that I wrote there. But the idea is like I just give you another point on the curve. Okay. And once you have 2 points, right, then it is easy. Once you have 2 points, it's easy to find the equation of a line going through the 2 points, right? So you can choose this line. You get this line connecting these 2 points on the curve, right? And and the idea or the hope is that if you start making this point approach, if you make Q approach P more and more, right, there is the limit of these lines that you're getting, right, like of these connecting lines, should be the tangent line. Okay, so we're going to try to find the tangent line as a limit, right, of all these like intermediate lines or lines that we're getting by moving a point on the curve around. Okay, is that making sense? So like the idea is like to find the slope, what we're going to do is compute the slopes of like these auxiliary lines And the slope that we actually care about is the limit of all the slopes as the point that you're using is approaching the one that you care about. Is that okay? Is that making sense? I'll write a picture in a on the iPad in a moment just to make this more clear. But let me go back. So here's the idea, so here's the idea of how to find the slope. Let me see if I can copy paste this picture to work with this one again. So the idea is that you find you have like the point x, which is this value of x, which is the one that you care about, and so you move a distance h from this point. Okay. And if you move a distance h from this point, then you get a new point on the curve, which is called q, which is x plus h, comma, f of x plus h, right? And then there will be this line connecting these 2 points. Is that making sense? Up to this point, so like this is like, think of this as an auxiliary point. And this is like some sort of like auxiliary line. So it's not a tangent line, but it's just like a line that will help us find the tangent line. Is that making sense? So far, so good? So the thing is that in principle, it is easier to find the slope of the blue line because you know the equation for the function. So what is the slope of this auxiliary line? Remember, it goes through P and Q, right? So when you have 2 points on a line, you can find its slope, right? So the slope, if you remember, is like this right over run formula. So it is a change in the y values of the points, right? So let's let me see, put it like this. Is that making sense? So for finding the slope of this line, what I'm looking is at the y values. I take the difference of the y values, and I look at the x values, and I take the difference of the x values, and that's the slope of this line. Is that okay? And so you see like that this slope is actually, if you look at it, there's not too much that you can simplify here, but at least you can simplify the denominator a little bit because this x cancels this x. So the slope, the formula for the slope in this equation or in this expression is f of x plus h minus f of x over h. Okay. Um, well, there is got a question on the chat. At the- like when for now, there will always be like a problem that will ask you to find these derivatives using the limit definition, which is I'm showing you. But well, the quiz, like today's quiz doesn't include derivatives, so it won't be here. But yeah, in general, once we have quizzes involving derivatives, you could use whatever rules I give you. Um, okay, so that's a slope, and then the idea is that if this is all going to work out, if you make again the distance between these 2 points, like the distance between these 2 points is h, right? The So the idea is that if you make h go to 0, right? By the way, this can also, I mean, I'm putting h as if it were positive, but it could also be negative, in which case, like the point would just be on the left side. That's kind of the same. It's just easier to draw the pictures where everything is positive, but that's just for convenience. So if you make h go to 0, what you would expect is the blue line to become closer and closer to the red line. So what we would like to say, or it is actually our definition for the slope of the tangent line is going to be the limit of these things, of these slopes as h approaches 0. So the slope of the tangent line is defined, slope of the tangent line okay? Is that making sense? So let's try to do, and again, I don't want to bombard you with a notation and bunch of definitions or new names. So let's just try to do this first in a couple of examples so that you see what the idea is, okay? And you'll see why this limit stuff that we have been doing was useful, and why we spend so much time using the limit stuff. So let's do some examples. Let's say, let's do the parabola just because we spent some time with that picture. So imagine that I had given you the equation of the parabola. Right, so I give you a point x, and I want to find the slope of this line, right? So if you follow the formula, right? Sorry, this should be x squared. I forgot to write it here. So f of x equals x squared here. So if you follow the formula for the slope, right? Well, that is a limit as h approaches 0 of f of x plus h minus f of x over h. But what does that mean? What does f of x plus h mean? It means replace x with x plus h in the formula for the function. But the formula for the function is just to square the variable, right? So what this means is actually x plus h squared, and f of x is just x squared, so you just get this. Is that making sense? What why this is this? Any questions about that? And then how do you find this limit? What would you do to find this limit? Now this is like a limit like the one we have been studying. Um, what could you do to find this limit out? Yes, you could do that. That's one option. There's another option as well. But that's a good, I mean, that would work, for sure. The other option that you could do is like, this is like a difference of square formulas in the numerator, right? Because it's like a squared minus b squared kind of. So if you do, so a is x plus h here. Is that making sense? And so what do you get if you get that? If you do that, what do you end up getting? You get h times x plus 2h divided by h, right? Sorry, 2x plus, I messed up the 2x plus h here divided by h. What can you do next? You can cancel the h that's in here with this one. So you get the limit as h approaches 0 of 2x plus h. And what is that limit? That limit is just 2x, right? Is that making sense? Are there questions about this so far, so good? So this is let me write this down again. This is very useful. What this is saying is that if you have a parabola, right? If you have a parabola and here you have the point x comma x squared, right? This line has slope 2x. Okay. So just to make two concrete examples. So imagine that I had chosen x to be, imagine I had chosen x to be 1, right? So if I had chosen x to be 1, this would be 1 comma 1, right? And so the slope in this case is what? What would be the value for the slope in this case? It's just 2, right? Because the slope is 2 times x. So it's just 2. And once you have the slope, what would be the equation of the line? Remember, the equation of the line is, what's the equation of a line? Is y minus y naught equals m times x minus x naught, where y naught, x naught are points on the line. So the equation of the line would be y minus 1 equals 2x minus 1. So that would be the equation of the tangent line. But on the other hand, if you had put like, let's take the parabola again. But now instead of like taking the value of x equals 1, I'll take the value x equals -2. So let me put here -2. Let me use a different color. So if this is -2, this is the point -2 comma 4, right? And now the tangent line should look like this. Hopefully you believe that. Okay. And then what is the slope of this green line? What is the slope of this line? For this value of x that we chose. It's just -4, good. So this is -4, and so the equation of the line is y minus 4 equals m, but m is -4 times x minus 2, I mean minus 2. So it's -2. So it's y minus 4 equals -4 times x plus 2. So that's the equation of the tangent line at that point. Well, I'm about to show you this in GeoGebra, but maybe let me stop first to see if there are any questions up to this point. Is that making sense so far so good? Not really. This is acceptable as the equation of the line. Yeah, you could write the line in this way if you want. This is fine. So just to go back to GeoGebra to show you that this actually does work the way it's intended. So right, like 1 point was 1 comma 1. That's the first one. And if you check your notes, the equation that I wrote for the tangent line in this case was y minus, let me change, well, I'll change it, which is there. So you see it does look like the way it's supposed to. Let me change the color of the conic because it was blue on the iPad. Okay. And this point is supposed to be red. So that's the equation of the line. And then you had this other point, which was -2 comma 4, which is in there, right? And it has its own tangent line, and the equation for that tangent line was y minus 4 equals minus 4x plus 2. So you see, it does look reasonable that that would be the tangent line. So if you like, the idea is like for the tangent lines, right? If you zoom in, like the graph, if you look at the graph, if you start zooming in, the difference between the curve and the line kind of starts disappearing, right? So the tangent line, you should think of it as an approximation to the curve, or the line that's closest to the curve at a specific point. So at this point P, the line that's closest to the curve or that gives you the direction of the curve is this pink line. But if you go to Q, if you go to Q, the line that's closest to the curve or in the direction of that curve is that green line. Is that making sense? But like the important thing is like these tangent lines, they do depend on the point that you choose. So if you choose a third point on the parabola, the equation of the tangent line would be different. But the important thing is like kind of like there's a single formula for the slope, which is just 2 times x. Is that okay? Are there any questions about this? Okay, so let me give you one example for you to think about, and then we'll discuss it together just to see if this is making sense. And then we'll do one more, and then I'll tell you some notations. Here's another example. So imagine that I had given you instead the function square root of x. And again, I give you like a point x here, and maybe you want to find the slope of the tangent line going through this point, right? So this slope, if you remember the formula, is going to be the limit as h goes to 0 of f of x plus h minus f of x divided by h. So that's the limit as h goes to 0 of root of x plus h minus root of x over h. So again, like hopefully this looks like familiar to the limit we have been studying until now. So try to find this limit. Let me give you like 3 minutes to think about it. It's very similar to the ones we have been doing. So let's take 3 minutes and then we'll discuss it. Um, so how do you find this limit? What do you have to do first? Yeah, good. You multiply by the conjugate. So that's why I'm choosing today to do these things first because it's still about finding limits, which you need to know for the exam. So still related to exam stuff. Although I wouldn't ask you to find the slope of the tangent line, but these limits that do show up are kind of similar to the ones we have been doing. Um, good. So you multiply by the conjugate, and that gives you like difference of square formula on the top. So it becomes x plus h minus x, and there's not much that can be simplified at the bottom. Okay, so far so good. And then what do you do once you get here? Well, you can simplify this x with this x goes away. And once you did that, then the h's cancel, right? So you get the limit as h approaches 0 of 1 over root of x plus h plus root of x. Is that making sense? And so when approaches 0, you just get root of x, so you get 1 over 2 root of x. Is that okay? Are there any questions about how I found this limit? So just to summarize what this means is that, to emphasize this, what this means is that if you look at the graph, so if you look at the graph of y equals root of x, right? Then the slope of this tangent line is 1 over 2 root of x. So for example, if you wanted x to be 4, right? If you had chosen x to be 4, if you choose x to be 4, then this gives you the point 4 comma 2, right? Because you're taking the square root on the graph. So the slope of this line, what is the slope? It would be 1 over 2 root of 4, and that's 1/4, right? So the equation of the line is y minus 2 equals 1/4 of x minus 4. Is that making sense? So just to maybe show you this in GeoGebra again. You take square root of x. I chose a point 4, 2, which is there. And I'm claiming that the equation of the line, of the tangent line, is y minus 2 equals 1/4, which is 0.25. So I'll write it like as 0.25 x minus 4. Okay. And there it is. And it does look like a tangent line. Right? And so that's the equation. And again, like the cool thing about this formula is that if I had chosen another value for x, like I still know the value for the slope because it's 1 over 2 root of x. So you can, like the good thing about finding the slope in this way is that it gives you like the slope for any point on the graph, not just like a single one. Just the slope can vary from point to point. Okay. And just to do one more example, then I'll go back to tell you a little bit more about this stuff that we're finding. the last one that's kind of interesting to do today is the this same thing but for sine of x. So this was a graph of sine of x, if you remember it. And then a similar story, you have a point x, you have now the point x comma sine of x. And you want the slope of the tangent line. So you want the slope, and the slope is going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, and what is that? Well, this is the limit as h approaches 0 of sine of x plus h minus sine of x divided by h. And then there was this a formula for the sine of of the sum of two numbers, which you may remember. Like, you don't need to remember this formula, so I'll just write it down. We will just use it in this in finding out this limit, but it's not one that I'm expecting you to remember. I would give you that formula, for example. But the sine of like alpha plus beta was like the sine of x times the cosine of h plus the cosine of x times the sine of h. So this thing becomes this thing. Okay, and now how can you now this is an important question. What would you do to try to simplify this limit? What's an option you could try? This is maybe less clear than the others, so how can you try to simplify it? But what could you do? Yeah, you kind of want to factor out a sine of x, but here's you have to be careful because sine of x is only on the first and third terms, but we should start there. So one way to think about this is that this is the limit as h approaches 0 of sine of x. If you factor out the sine of x, you get sine of x times cosine of h minus 1 plus cosine of ax sine of h. Okay, that's actually it's convenient to write it out this way. And, this is like, you can split this fraction into a sum of two fractions, which is actually more useful. Because hopefully the ones that I'm putting in parentheses, they look more familiar. So what's anyone like this one looks similar? Here, remember the limit depends on age, right? So it's a limit in terms of age. So this should be, it is kind of like if you called H theta, which you could for psychological purposes, you have the limit as theta approaches zero of sine of theta over theta, right? And what is this one? Um, no, sine of theta over theta, yeah, it's a slightly different value, which you need to know for today's quiz. It was 1. Sine of theta over theta was 1, yeah. And what was the limit? What was the limit for this one? What was the limit of cosine of theta minus 1 over theta? Um, it was 0. Yes. So you get sine of x times 0 plus cosine of x times 1. So you just get cosine of x. So that's kind of fun, especially if you have never seen this before. It's kind of cute. What this is saying is that if you have like if you have the sine function, right? Then the slope and you have here x, then the slope of this tangent line is going to be cosine of x. Okay. Any questions about this? So far so good. So now let me give you some notation. Now that I have done some examples, I can give you a little bit more notation. So I don't know if there are any questions up to this point. Before just give you some more information about these things. So here's the definition. These the slopes that we have been finding are called the first derivative of the function. So if f of x is a function, the slope of the tangent line to this function is called the first derivative. And it is denoted and it is written as f prime of x. Okay, so when like just to make a picture, what I'm saying is that here you have the graph of a function. and you had the point x comma f of x. So the slope, oops, let me see if I can draw it a little bit better. So the slope of this tangent line, instead of just calling it slope, you call it f prime of x. Okay. So it's kind of like a new note. It's kind of for now not that clear why would you do that, but it's we'll see after next week after the exam that there are other notations you can give to this first derivative, which kind of suggests which gives you like useful ways to remember certain things about these slopes and things like that. So for now, it's just like a short, a different way of saying slope, but you'll see later that it actually has other important benefits to having a separate notation for this. So just to make a table of so which three functions have we studied thus far? We studied x squared, right? We studied root of x, and we studied sine of x, right? So if f of x equals x squared, right? If you remember, we found the formula for the slope, which is 2x. When f of x was root of x, we found the formula for the slope was 1 over 2 root of x, right? And when f of x was sine of x, the formula for the slope was cosine of x. So in that way, these are like the first derivatives we have found up to this point using the limit definition. And again, like maybe I should write it here, like next to it, so that it's more useful, a better reminder. Is that making sense? Okay. Any questions up to this point? Like the thing is like so a lot of like the beginning of what we're going to start to do in this stuff about derivatives or finding slope is just to find formulas for the slopes of a lot of functions. So a lot of energy will be spent just in finding like these formulas, not just in finding these formulas, not just in these cases, but in more complicated cases. But at least there are a couple of like of building blocks that I can give you as a table. And then what we'll do next time after the exam is just to discuss like once you have these building blocks, how do you build more complicated how do you find more complicated derivatives? So in a sense, think of this like as if you like chemistry, like as an atomic table, right? Like these are kind of like the uh what like we're kind of building molecules that like out of some basic atoms. So these are kind of like the elements in our periodic table, and then I will give you some rules for finding the derivatives for these slopes in more complicated cases. So, but let me just So here like some basic derivatives. So the first one is like the first one is like a generalization of x squared and root of x, which is the derivative of x to the n. So the derivative of x to the n is going to be xn times x to the n minus 1. Okay? Well, let me put it this way. I want to write some examples below it. So let me give you put it like as like the power rule of if f of x is x to the n, then f prime of x is n to the xn minus 1. Okay, so what that means, like n here is the exponent. So like let me give you some examples. So let's say n equals 2. So f of x would be n x squared, right? So if you look at the formula for this derivative, what this is saying is that the exponent comes down. So you bring the exponent down in front of the x, right? And you decrease the exponent by 1. And so you end up with 2x, which is what we had found before, right? Here's another one. What if n equals 1/2? So you would f of x would be x to the 1/2, which is root of x, okay? But what is f prime of x? If you look at this, the exponent comes down, and then x, the exponent of x gets decreased by 1. And this is 1/2 root of x. Is that making sense? What I'm saying? Are there any questions about this? Just to make sure you this is making sense. Let's say if I gave you instead and to be like 5, just to make sure that this is okay. So what would be the derivative for x to the 5? According to the power rule. Yeah, good. The exponent comes down. It's very easy to remember. The exponent comes down in front of x, and then the exponent gets decreased by 1. So 5 minus 1 is 4. Okay? And again, what this means is that if the function is x to the 5, the slope of the tangent line is 5x to the 4. Okay, so again, these are giving you formulas for the slopes at your favorite point on the curve. And it actually also works for negative values, for negative exponents. So for example, here's another one. What if n had been like -1? If n had been -1, so you're looking at f of x, which is x to the -1, which is 1 over x, right? And the power rule says, what does it say? It says, bring this exponent down, okay? So when you bring it down, it becomes -1, so minus x, and then decrease this exponent by 1, right? Subtract 1 from it. So -1 minus 1 is minus x to the -2, and that's -1 over x squared. Is that making sense? In fact, I mean, like again, after the exam, we'll see that there are other ways to find some of these formulas, which is kind of fun to to check that they actually we're not making anything crazy. So there will be other ways. It's like if you didn't want to use the power rule, there are other ways to find these formulas, and I'll explain to you how. Because what will happen is that I'll give you a bunch of formulas for finding derivatives, and then again, it's really like building like it's kind of like building a dish. Like you have a bunch of recipes, and then you have to kind of decide how to combine these recipes or formulas to build like your molecule or like your favorite food dish. So it is kind of like building blocks. So I'm giving you some building blocks, and then you have to kind of work with them. But for now, we're starting slow. So I'm just giving you like the really basic ones, but you'll see later that with these extra rules, you can come up with the formulas for very complicated things. Okay. Here's here's another important of case, which is like the trigonometric functions. And again, I won't give you all of them right now. I'll give you more later once we have more rules to compute them. But here, like some basic sine and cosine, right? So if f of x is sine of x, oops, f prime of x, right? This is the one we just found, right? It is cosine of x. And here's the cool thing. If f of x is cosine of x, right? F prime of x, and that actually you can check with the limit definition. So you can compute the limit and check it for yourself. It's kind of very similar to how we did it for sine. You just have to remember the formula for the cosine of like the sum of two angles. So the way in which you typically say this is that the derivative of sine is cosine, but the derivative of cosine is minus sine. So there's a minus here. Okay, so again, like the first one we found before a couple minutes ago, and the second one, if you want to try it, it is not that different from the case of sine. You just have to use the formula for cosine of alpha plus beta. But again, like all of these that I'm giving you, you can kind of like it is kind of like it's a toolkit, so you can memorize it. I mean, you should memorize them actually. It's important to have them like to know what they are, um, fro- without having to rederive them using the limit from scratch because that would take forever. So it's important to to know the answer from scratch. I mean, like to just know the answer. Here's like a very simple one, but it's still kind of like useful to like write down explicitly. What's the derivative of a constant function? It's kind of silly, but it is still useful to have. So for example, like f of x equals what do you think the derivative of a constant function should be? It is a kind of like a real weird question, but yeah. So just to give you an idea, like here's like f of x equals 3, for example. So the thing is that this graph is already aligned, right? So the tangent line should actually be itself, if that makes sense, right? Like if you're trying to find the tangent line to a function, but the function is already aligned, the tangent line is just itself, right? So the function, like the tangent line is the same function, but then what's the slope of a horizontal line? The slope of a horizontal line is 0. So you can actually do this with the limit definition, but it's just better to understand it from the picture. So if f of x is constant, meaning that it doesn't depend on x, f prime of x is just 0. Because like slope of a horizontal line is 0. Okay? So again, it's kind of like a theory question, but a kind of more like a conceptual vibe question because it the calculation itself is not too difficult, like if you use a limit definition. But it is more like trying to understand what this means in terms of the graph. And so the tangent line should just be the same line, but for horizontal lines, like the slopes are 0. And maybe just to give you the last one before we finish for today, because like the next thing I want to do is after we come back next week after the exam, like I'll give you like all these rules for finding derivatives. The last one I wanted to give you is the exponential function. So if you have e to the x, actually the derivative, the slope of e to the x is e to the x, meaning that the value of the function itself gives you the slope of the tangent line. So that should be like extremely unusual, and in fact, it's very unusual. It is the only case where this happens. So they are the same. So just to make it as a picture, just to explain, I mean, again, this is a graph of e to the x, and if you had like a point x comma e to the x here, the slope of this tangent line will be e to the x. That's what this is saying. And again, this is actually, this is one of those limits which is highly non-obvious why it works, and trying to explain why it actually is what this is, why this actually works would take us, it's like it would require like a detour into how do you define the exponential function and things like that. It's actually like a complicated thing to prove. Um, so but it is very important, and it is a reason why the exponential function becomes so useful. So once we get to applications involving derivatives, you'll see that the exponential function like plays a big role because of this property that to find its derivative is just coincides with the function itself. Okay, so is the if yeah, I mean probably it's not a good moment to get to these applications now, but like it is related to like population growth, radioactive decay. There are a bunch of properties, things that you can model with the exponential function, and the reason why the exponential function works is because of this property of the derivative. And again, this will become more clear later on. Okay, but yeah, I think this is what I wanted to tell you for today to give you a chance to do the quiz. Are there any questions about this before I finish the Zoom meeting? Okay, yeah. So I'm about to make the quizzes available on the quiz available on Canvas. So if you log out in 30 seconds, you should be able to see it and start taking it if you want. So let me stop sharing here and let me make the quiz available. Yeah, you should be able to access it now and upload the solutions and everything. So yeah, good luck. I'll see you on Monday, but if you have questions, just email me in the meantime.
I'm just having an issue leaving on my phone.
Sorry?
If I'm just here, I'm just having an issue leaving on my phone, but
Oh
and
yeah,
I'm
yeah,
about to
you're
take
good.
the quiz. Okay.
Perfect, perfect. Don't worry. Yeah, you're good.